Okay, so we're going to look at some collisions. These are 1D collisions, objects smashing into one another, maybe sticking together, or hitting one and the other one bouncing off. We're going to look at some special cases. And the first case that we're going to look at is, well, let's go over for a second. Let's talk about the different kinds of collisions that we can have. First is an elastic collision. An elastic collision is one that conserves momentum. Momentum is always conserved, but this one also conserves kinetic energy. So kinetic energy is conserved. We can also have an inelastic collision, or we'll talk about an inelastic collision. Momentum is conserved, kinetic energy is not conserved. Okay? So this is where an object interacts with another object. Maybe it gets deformed, or something happens. We'll talk about a perfectly inelastic collision where the two objects come together and they stick, that kind of thing. So we have an elastic collision. Some people may call it a perfectly elastic collision that momentum's always conserved and kinetic energy is conserved. Then you can have an inelastic collision where kinetic energy is not conserved, momentum is always conserved, and we'll have another one that is a subset of inelastic, which is a perfectly inelastic, which is where the two objects actually stick together. So I'm going to look at a special case of an elastic collision. So this is a collision where kinetic energy is conserved, and the first case we're going to do is a so-called stationary elastic collision. Now these are one-dimensional collisions. We will have to pay attention to the SIGN of the velocity because that's going to make a difference. Remember, momentum is a vector, so we need to know which way the object is moving, as far as if it's in the positive x direction or the negative x direction, or whatever we want to call that direction. So as always, I'll make this the positive x direction, and we'll look at some special cases. Stationary means that one of the objects, which we're going to make the one on the right stationary, so its initial velocity will be 0, okay? So let's look at a case where you've got this would be M2, it's stationary, and here's M1, and this is V1 initial, okay? So let's say that M1 is less than M2. What do you think's going to happen? Well, this has less mass than this. This is going to come in. It's going to bounce off, depending on the relative masses and the velocity. It's going to bounce off and go in the other direction, and this one's going to go forward a little bit. Okay? So this is before the collision, and after the collision, you would have something like this. Here's M1. This would be V1 final. Here's M2. And this would be V2 final. So I would expect, if M1 is less than M2, then I would expect that V1 final is going to be negative and V2 final is going to be positive. Okay? So that's M1 less than M2. What happens if M1 is greater than M2? So here's M1, let's make it big. Here's M2, remember this is stationary. This is before the collision, M2 is stationary. Here's V1 initial. This is before, and M1 is greater than M2. So what do you think's going to happen? Here's what I think's going to happen just from everyday experience. M1's going to come in, smash into M2. It's going to go that way, and M1's going to keep going. Okay? So after the collision, you have M1. I'm not going to draw it as big. V1 final. And M2, V2 final. So I would say that if M2 goes in that direction, it has a positive final velocity, and M1 also has a positive final velocity. Okay? This is like a big massive object coming in, hitting a little small object, and that thing takes off. What happens if M1 is equal to M2? So here's M1, here's M2, V1 initial, this is before the collision, okay? Well, let's put M1 is equal to M2 over here. In this case, the only way that momentum can be conserved, and we can go through the equations, but the only way that momentum can be conserved is if M1 strikes M2, M1 stops, and M2 takes off with the same final velocity as the initial velocity of M1. So after the collision, I would expect M1 to be stationary, and M2, my 2's aren't very good, there's M2, and this is V2 final, and V1 final is equal to 0. Okay, this is after the collision. All right. I'm not going to derive the equations, right? I'm going to just give you the equation for the stationary elastic, and then we're going to derive the equations for a little bit more complicated problem. So the equations for the stationary elastic collision are these. V1 final is equal to M1 minus M2 divided by M1 plus M2 times V1 initial. V2 final is equal to 2M1 divided by M1 plus M2 times V2 initial. Okay? So let's look at the cases that I just talked about. In the first case that I talked about, we said that M1 is less than M2. Well, if M1 is less than M2, that gives you a negative, and that's what we saw, that V1 final was in that opposite direction. You got a negative of V1 initial. V1 initial was in the positive x direction, so you got a negative. V2 final is always going to be positive in these stationary elastic collisions unless M1 equals M2. Well, no. If M2 equals M1, then V2 final will equal V1 initial. So in the case that I just talked about where M1 is less than M2, all right, you got V2 initial, which what did I do here? This is not V2 initial. This is V1 initial. That wouldn't make sense. Okay, there's V1 initial. Sorry about that. So in this case, V2 final, M1 is less than M2, and you get V2 final, which is positive. V1 initial was positive, so this is positive. Okay? Then I had the case where M1 is greater than M2. Look what happens there. If M1 is greater than M2, then you have a positive numerator here times a positive V1 initial. You get a positive V1 final. That's exactly what we saw. We saw that M1 kept going and V2 final was positive as well. I'm not thinking about magnitudes as far as the magnitudes of the velocities, but you get a positive velocity for V2 final. What happened in the case where M1 was equal to M2? When M1 is equal to M2, this term is 0. You get V1 final equal to 0, and then if M1 is equal to M2, then this just becomes 1, and you get V2 final equal to V1 initial. And in the homework, you'll do some of these problems based on this, so you'll see how these equations work. I'm not going to do an example right now. I'm going to look at a different type of collision and do an example for that. So I'm going to look at a little more complicated case, and I'll go through some of the mathematics for that, some of the algebra. And this is just in general, an elastic collision. Okay? So let's take two masses. Here's V1 initial, that's M1, and here's M2, and they are traveling like this. Here's V2 initial, okay? So they come together, there's no loss of kinetic energy, momentum is conserved as always. What's going to happen? Well, it depends on the relative masses and it depends on the relative velocities. Several things could happen. You could have this whole system move this way, you could have them come in and bounce off, you could have it move lots of different ways and lots of different velocities, depending on the relative masses and the relative velocities. But we know that kinetic energy is conserved, so I'll write that down. You have that 1/2 M1 V1 initial, lots of subscripts and superscripts, okay? 1/2 M1 V1 initial squared, that's the kinetic energy of M1, plus 1/2 M2 V2 initial squared. That's the kinetic energy of M2. That's prior to the collision. Kinetic energy is conserved, so post-collision you have 1/2 M1 V1 final squared plus 1/2 M2 V2 final squared. That's the kinetic energy post-collision. Those must be equal to one another. All the 1/2s cancel, okay? And you can do a little algebra and you get M1 times V1 initial plus V1 final times V1 initial minus V1 final equals M2. This just comes from collecting terms, undoing the squares, moving things around. So at M2, V2 final plus V2 initial times V2 final minus V2 initial. I don't know if you can see that, but that's V2 final minus V2 initial. Okay? I'm going to leave that up there. Momentum. So this is conservation of kinetic energy. For momentum, it's always conserved. So we have that M1, this is momentum conservation. We have M1 V1 initial plus M2 V2 initial is equal to M1 V1 final plus M2 V2 final. Okay? Remember, there are signs involved. These have signs depending on their relative velocity, or depending on their velocities. This has a negative velocity, this has a positive velocity. Okay, we'll see how that works when we figure out the final result for these equations. Okay? So I can collect terms here in terms of V1 initial and V1 final, and I get M1 V1 initial minus V1 final, that's just moving this over here, equals M2 V2 final minus V2 initial. Okay? Look what I have here. I have V1 initial minus V1 final times M1. Down here, one of the factors is exactly like this. I have M1 V1 initial minus V1 final. This came from kinetic energy. This side, M2 V2 final minus V2 initial. M2 V2 final minus V2 initial. This implies that V1 initial plus V1 final must equal V2 final plus V2 initial. That's the only way you can satisfy these equations, both of these equations. Okay? So this implies that V1 initial plus V1 final is equal to V2 final plus V2 initial. All right, we have that. Now, I can go back up, let's see, I'll go, I've already erased it, but you get two equations, you add them together, and I'll show you what they are. Okay, so we have that M1 V1 initial minus M1 V1 final is equal to M2 V2 final minus M2 V2 initial and M1 V1 initial plus M1 V1 final is equal to M2 V2 initial plus M2 V2 final. Okay? So I'll add those equations together. If we add these two, what I'm going to do is I'm going to solve for V2 final. By adding these two, I can get rid of V1 final because I have a minus M1 V1 final and a plus M1 V1 final. On the left side, you get 2 M1 V1 initial is equal to, when you add these together, okay, you get, I think I made a mistake. Yeah, sorry about that. This is, that was looking really weird. This is M1 and M1. Okay, I had to write in the notes. All right, you get M1 minus M2 times V2 initial. M1 minus M2 times V2 initial plus M1 plus M2 times V2 final. Okay? So I have it, when I'm adding these equations, I get M1 minus M2 times V2 initial and M1 plus M2 times V2 final. I'll solve this for V2 final. I'm going to go ahead and erase this. And V2 final is equal to 2M1, you just divide through by M1 plus M2 over M1 plus M2 times V1 initial plus M2 minus M1. The sign changed because I moved it to the other side. M1 plus M2. Let me go ahead and put these in parentheses. Times V2 initial. So that's the way you find V2 final. You can do the same thing for V1 final. You swap these around. Well, the math swaps them around the algebra. So V1 final is equal to M1 minus M2 over M1 plus M2 times V1 initial plus 2M2 over M1 plus M2 times V2 initial. So these are the two equations that you need to find the final velocities of the two objects after the collision. And you do have to pay attention to the sign of these velocities. Okay? The way I've drawn it, V2 initial would be negative, V1 initial would be positive. So let's look at an example. I'll do a quick numerical example. Maybe one that's not so obvious. Okay, so you've got these written down, and I'll use those equations to calculate the final velocities for a particular case. So let's say we have a 1 kilogram object traveling at 2 meters per second. To the right, this is the positive direction. I'll make it X, it doesn't matter. And a 2 kilogram object colliding with it at 3 meters per second. Okay? So maybe you can tell, I mean, you got a heavier object going faster and a lighter object going slower. Their speeds, I don't know. Let's see what the equations say. So plugging into that equation that I just gave you for V1 final, V1 final is equal to M1, that's 1 kilogram, minus M2, 2 kilograms, divided by the sum of their masses, which is 3 kilograms, times V1 initial, 2 meters per second, plus 2M2, so that's 2 times 2 kilograms, divided by the sum of their masses, which is 3 kilograms. Here's where you can get in trouble. Multiplied by V2 initial. V2 initial is negative 3 meters per second. Okay? This works out to be, let's see what we have here. So this is negative 1/3 times 2 meters per second. So that's negative 2 over 3 meters per second. Plus, the 3's cancel and you get a negative 4 meters per second. And that works out to be negative 4 2/3. So that's negative 14 over 3 meters per second. That's V1 final. What happens? They come together, they exchange energy, momentum is conserved, and this one bounces off and goes in the negative direction. That would be the 1 kilogram mass. Goes in the negative direction at negative 14 over 3 meters per second. That's V1 final. Let's plug in and see what happens to M2, which is the 2 kilogram mass. So V2 final is equal to 2M1, so that's 2 times 1 kilogram, divided by their sum, which is 3 kilograms, times V1 initial, which is 2 meters per second, plus M2 minus M1, so 2 kilograms minus 1 kilogram, divided by the sum of their masses, which is 3 kilograms, times negative 3 meters per second. Okay? So this is equal to 4 over 3 meters per second. This is equal to 1 over 3 times negative 3, so that's a minus 1 meter per second, and that gives you 1/3. So what happens to M2, which is the 2 kilogram mass? It, because of the collision, it stops and goes back very slowly in the positive X direction. it's going at 1/3 meters per second. It started out at 3 meters per second in this direction, and it ends up going 1/3 meter per second in that direction. And that's the way we'll handle these elastic collisions. We'll do some more examples and some homework problems with those. I want to talk about one other type collision, which is the perfectly inelastic. For the perfectly inelastic collision, kinetic energy is definitely not conserved. Okay? Let's say that you have two objects, M1, here's V1 initial, and M2, here's V2 initial. Okay? And I am putting the little vector sign over them because by conservation of momentum, P1 initial, which is the momentum of M1, plus P2 initial, that's the momentum of M2, that's going to equal the total momentum after the collision. This is a perfectly inelastic. So that means that the two objects come together and stick. All right? This is M1 plus M2. What's the final momentum? Well, it's M1 plus M2 times V center of mass. And if it's a one-dimensional case, that's really simple because you only have to deal with just the positive and negative signs for the momenta. Okay? So let's look at a case where M1 is equal to M2. A real simple case. Well, and I'm going to use, well, let's make it really, really simple. Let's say M1 is equal to M2 and V1 initial equals V2 initial. Magnitude-wise. So P1 initial, I'm going to drop the vector sign, it's a one-dimensional case, is M1 V1 initial. Okay? P2 initial is equal to M2 V2 initial, but that's negative. All right, I'm going to make that negative, and this is a magnitude. But M1 equals M2, and the magnitude of V1 initial equals the magnitude of V2 initial. So this P1 initial, I'll just call it MV initial, and P2 initial is equal to negative MV initial. Can you see what's going to happen when I add these two momenta together? Then you get that P1 initial plus P2 initial is equal to 0. If you have two objects that are the same mass and traveling at the same magnitude of velocity at one another, they just come together and they stick. That's the only way momentum can be conserved. The momentum of the system, if M1 equals M2 and their magnitudes of their velocities are the same, the momentum of the system is 0. So they just come together and they stick. If I had an air track, I could show you that. Maybe I can come up with something. Okay. So that's it for right now. Read, do some problems. See you next time.